In 1815, with Europe at war, 4 young Germans decided to do a particularly foolhardy experiment, one which would transform their lives and ours as well. One of them, a pharmacist, had created some intriguing crystals, which he carefully measured out. He was keen to see what effects they would have on his body. He dissolved them in alcohol and then diluted it with water. Since the crystals had recently been made and only previously tested on dogs, they had very little idea of what was going to happen. The answer was not much, so they did it again. Prost! This time there was pounding headache, nausea and extreme flushing. So naturally, they decided to go even more extreme. They put the crystals directly on their tongues and washed them down with another shot of alcohol. Their leader, Friedrich Zertner, describes falling to the ground semi-conscious, in terrible pain and fingers twitching with every heartbeat. Somehow he managed to crawl his way over to a bottle of really strong vinegar. He swallowed it down, and the rest he poured into the mouths of his unconscious assistants. They were all violently sick. Zertner had saved their lives by making them vomit, but he noted that for the next few days they continued feeling ill, aches, sickness and constipation. Swallowing the crystals had produced classic symptoms of opium overdose. Zertner was thrilled. He was the first person ever to extract the essence of opium, a white powder that he called morphium. He had given birth to a whole new science and opened a Pandora's box of good and evil. This series tells the extraordinary story of what Zertner unleashed. The remarkable medicines which today protect us against devastating disease. Just over there is a monster of biblical proportions, the smallpox virus. And the agonies of mortal life. I have here a big lump of raw opium. You almost want to lick it. Drugs that can be terrifyingly lethal. This is the most poisonous substance known to man. Or incredibly pleasurable. Oh, yes. Blimey, wow. It's a story of 2 centuries of greed, luck, and genius. In this program, I'm going to be telling the remarkable stories of the men who abolished pain, and by doing so created the world's most popular, desirable, and addictive drugs. This is such an odd and unnatural thing to do. I'm not sure I'm going to be able to do it. Let's see. Okay. Ah, God, that is just absolutely horrible. I'm just pushing a needle right through my hand. I don't know if it's got through the other end. Sticking out there. Ah! This is only possible because my hand has been numbed with local anesthetic. So the fact that I can do that is a testimony, if you like, to modern medicine. 200 years ago, we had almost nothing. We had a few herbal medicines. If you're having your teeth pulled out or your leg cut off, then you were going to be in an awful lot of pain. Pain is such a visceral thing that it's not surprising that the quest to find a way to control it has been such a driving force in the history of drugs. For centuries, there was only one substance that could reliably relieve pain: opium.
A resin extracted from poppies, it is one of mankind's oldest and most addictive drugs. Yet opium would give rise to today's giant pharmaceutical industry.
Opium's always been popular. It's always been very easy to tell what opium does because it acts in a very obvious way and it acts very quickly. The Sumerians called it the joy plant.
By the beginning of the 19th century, opium was widely available in Europe. It was particularly popular when dissolved in alcohol as a medicine called laudanum. Trouble is, the raw material was expensive and it was unreliable. So no wonder pharmacists began to ask themselves, what exactly is in opium that gives it its seemingly magical qualities? One of those pharmacists was the 20-year-old German Friedrich Zertener, whose attempts to produce morphium nearly ended in his death and the death of all his assistants. His experiments would unlock the key, not just to pain relief, but to all modern medicines. It took Zertener 2 years of trial and painful error before he discovered how to extract morphium from opium resin. I'm hoping to do it in rather less time than that, but because morphium is now a Class A drug, I'm going to have to do it in licensed premises. Zertener would have started with raw opium, which comes from the sap of the poppy. Now, I have an enormous great block of the stuff here. Still smells sort of yeasty. Time to extract morphium. First, Zertener added a standard solvent, alcohol. The alcohol should already be beginning to extract the chemicals from the raw opium. This, in essence, is laudanum, the sort of tonic they used in the 19th century. Gave it to squawking babies.
One of the ideas which actually comes from alchemy is the idea that there might be some active principle, something that lay at the heart of your substance, which gave it its power. And from there, it's actually not a huge step to say, well, what if we take away the alcohol? What are we left with? You know, are we left with that fundamental principle?
The first thing he managed to extract was a substance that was acidic. He tried it on dogs, and absolutely nothing happened. Instead of giving up, Zertener tried doing something no one else had previously attempted. The received wisdom was the only really important chemicals in plants were sharp-tasting acids. But Zertener decided to see if he could extract an alkaline chemical, the opposite of an acid, from opium. He was exploring the unknown. When you actually try and do it with modern equipment, it gives you a huge respect for what they were doing back then, because every stage would last weeks, and he obviously had no real idea what he was doing. Finally, around 1803, he got this sludgy precipitate. From this very unpromising substance, Zertener managed to extract some white crystals. When he gave these to a dog, the dog became sleepy, trembled, and then died. Zertener was absolutely thrilled. He published and sat back, waiting for the applause, which never came. It seems that people just weren't that interested in the workings of a young man doing his bit in a small back room. It was not until 10 years later, when Zertener purified and took the morphium himself, with his 3 assistants, that his dramatic discovery finally caught the attention of early chemists.
Gay-Lussac, who was a doyen of chemistry in Paris, probably the greatest chemist in the world of his day, he decided that this paper that had been brought to his attention should be translated into French and published, and therefore went round the world, and the world knew about this isolation. That was so important.
In extracting the active ingredient of opium, Zertener had launched a new age of discovery. He had shown that the powers of herbal remedies could be captured in a chemical form, measured out and quantified as a dose. He had also revealed a whole new world of previously unsuspected chemicals hiding in plants. They were to become our first real medicines. They decided to call these new chemicals they were getting out of plants the alkaloids. They also decided to give them the name ene, I-N-E at the end. And so Zettner's white powder became not morphium, but morphine.
The isolation of morphine was the single most important event that has ever occurred in drug discovery. Far more important than the introduction of penicillin in terms of advancing the science.
The extraction of morphine was such a big moment in the history of medicine because once you had the pure chemical, you could give it in a controlled and measured dose. You're no longer dependent on the vagaries of whatever plant you happen to be eating. It also meant they could extract dozens of different alkaloids. Nature's medicine cabinet was flung wide open. It turned out that alkaloids are the reason why many herbal remedies are effective. Being the plant's own defense against herbivores, a lot were bitter tasting and poisonous. But once isolated, we could start to use them, and not just as painkillers. Now I have here my favorite drug of abuse, caffeine. Other famous alkaloids include nicotine and the malaria drug quinine. And here's another I take from time to time. Codeine was another powerful painkiller which was extracted from the poppy. Codeine, like morphine, works by modulating the way that the brain perceives pain. Surprisingly, we are only now beginning to understand how these so-called opiate drugs work. Normally, raw nerve endings trigger an electrical signal, which travels to the spine. There, it's converted into a chemical signal, which crosses into other nerves, which then transmit the message to the brain. Once your brain has received that pain message, it can decide to tone it down or indeed switch it off entirely. It does that via another set of nerves that send a signal down the spine, and that interrupts the incoming pain message. Our brains typically activate this pain-relieving pathway in times of extreme stress. There are a number of different points along the pain pathway where you can turn the pain response down, and the opiates interact with quite a few of them. For example, they make the brain switch on the pain-blocking pathways I've just described. They also act in the brain to reduce the impact of any pain messages that get through. There's even recent evidence they can dull the raw nerve endings at the site of pain. It's no wonder they're so effective. The opiates are wonderful painkillers, but they do have significant side effects. Constipation, vomiting, addiction, and if they depress your breathing, death. Plants from all over the world were soon being examined for alkaloids that might rival the opiates. One plant from South America did indeed contain a substance with extraordinary pain-killing properties. But like morphine, it came with a heavy price. This white powder is an alkaloid extracted from these leaves. And these are the coca leaves. They are a well-known stimulant in South America, which means that this is cocaine, better known as cocaine. Cocaine was added to wines, which were promoted by the Pope. Soft drinks for those who disapproved of alcohol, and soothing drops and lozenges. But it was cocaine's reputation for combating hunger and fatigue that led a curious Austrian doctor called Sigmund Freud to investigate its effects further. Sigmund Freud was then a neurologist in Vienna. This was well before he developed psychoanalysis. And he got extremely interested in cocaine, which he called a magical drug, and which he prescribed to his patients for a whole range of ailments, including, ironically enough, morphine addiction. He sent samples of cocaine to a number of his colleagues, including a trainee eye surgeon called Karl Köhler. Köhler had been using morphine and other substances to try and alleviate the searing agony of eye surgery. But nothing had worked. Köhler tasted some cocaine, and he noticed that the tip of his tongue went numb. And he thought to himself, that's interesting. What would happen if I put cocaine into my eye? Well, he tried it out on a frog and a dog, and they seemed to be fine. So he then decided to try it out on himself. What he did, he and a colleague, is they got cocaine dissolved in water, and they dripped some into their eyes. Oh, God, that stings a bit. And then they got a nice sharp pin, and they sort of stabbed their own eyes. Now, I'm not going to do that. It sounds insanely dangerous. I'm going to use this instead. Oh, that's weird. I could just about see it bend then. Totally numb. This was extraordinary. Whereas the opiates numbed pain, cocaine is what we now call an anesthetic, which literally means without sensation. Cocaine stops nerves from firing, from sending signals, and affects not just the pain-detecting nerves, but all of them, which is why it makes the eye or tongue feel completely numb. Cocaine made complicated eye surgery possible. This stomach-churning footage from 1917 shows a cataract operation performed after putting in a few drops of cocaine. It would once have been attempted without pain relief. When cocaine gets to the blood and to the brain, there it acts very like the opiates, and that means it can be a drug of abuse. It's not very much used these days, but its derivatives certainly are. They form the basis of many local anesthetics. And as somebody who's had their teeth drilled more times than I care to remember, I'm hugely grateful to Dr. Köhler, or Coca Köhler, as he was sometimes called. But plants could not provide the level of general anesthesia required to make extensive pain-free surgery possible. In the good old days, patients weren't even allowed opium because pain was thought to be good for you.
Pain was understood as an essential component in terms of surgery. So although surgeons were concerned about the effects of pain on patients in terms of bearability, in terms of keeping a patient alive during an operation, it was regarded as part of the package.
A world where surgeons in frock coats committed acts of unspeakable horror would be changed by a dentist's chance discovery. But it was a breakthrough that was a long time coming. Throughout the 18th century, chemists had been experimenting with everything they could lay their hands on, from plants to rocks. They were particularly interested in creating gases. One of the gases they produced, they did by heating up ammonium nitrate. Now, this gas was said to be incredibly poisonous. So it's surprising that a young chemist called Humphrey Davy was so keen not just to collect it, but also inhale it.
It's very hard, I think, to get back into the head of an 18th or 19th century chemist. And that's partly because there was so much self-experimentation that went on. Now, gases, you inhaled them, and these airs, as they called, were at one point sort of regarded as possibly panaceas, solutions for big medical problems. And the way in which they tested them was on themselves.
The young Humphrey Davy was desperate to make his name, which is probably why, despite the risks, he experimented with this new, potentially lethal gas. It was a foolhardy thing to do. I am doing it under carefully controlled conditions.
Ooh, nothing yet. Yes, there is. Okay. Now, he records it in his diaries that he started off feeling sort of sleepy and splenic, but after a couple of blasts of it, he started to want to dance around the room. Oh, yes, I'm feeling it now. Lightheaded.
Yeah, I can see why they call it laughing gas. He also wrote other things in his notebooks, which I've entirely forgotten now. His notebooks, yes. He was writing something about... Ooh, yes, there it goes. Now, one of the things that he noticed and then wrote about, not in his notebooks later, is its effects on pain, that apparently it reduced it. Ooh, yeah, that's actually all right. Davy published his discovery that nitrous oxide relieved pain and even stated its potential in surgery. And yet, tragically, he did nothing more about it. For the next few decades, surgeons went on operating on fully conscious patients, and nitrous oxide was used mainly as a recreational drug for laughing gas parties. It was at one of these in America that a young dentist called Horace Wells came across the gas and saw how effective it was at dulling pain. Because his days were spent yanking out teeth, it made a deep impression.
He was horrified by pain. And there was nothing new about that surgeons, often the most brilliant surgeons, were repulsed by what they had to do. That if you had to operate on someone, if you had to cut into them without anaesthetics, it was an awful thing. They would vomit with fear and revulsion prior to doing an operation.
After experimenting, first on himself and then on some patients, Wells realised he had stumbled across something truly miraculous, a gas that could open the way to pain-free surgery. So, he headed to Harvard Medical School in Boston to tell the elite surgeons what he had found. He invited a former partner of his, William Morton, who was also studying at the medical school, to accompany him and share his triumph. On a cold winter's night in 1845, Wells and Morton appeared before a packed audience of doctors and medical students. Now, one of the medical students had a problem with his teeth, so he was summoned forward. He was given a good old blast of nitrous oxide from a bag that Wells had brought with him, and then Wells attempted to extract his painful tooth with a pair of pliers. No one's entirely clear what happened next, but the student made a noise. The audience interpreted that as a cry of pain, and soon there were hisses and cries of "humbug, humbug," which was a deadly medical insult. Utterly humiliated, Morton and Wells packed their bags and they left.
No one had imagined that anaesthesia could exist, and I think that's why Wells failed in his demonstration of nitrous oxide, because they found the very idea that pain was optional, that pain could be deleted, erased from the world, so intrinsically fraudulent that they were predisposed to reach that conclusion.
Wells was broken by this failure and would later commit suicide. But Morton had seen the commercial potential.
His real motivation for trying to find a decent method of pain relief for dental work was actually sort of to find a way of expanding his business, because by that stage, new technology produced sets of artificial teeth. So rather than just individual teeth, a patient could have a whole set fitted. But obviously, to have rotten stumps and roots extracted without pain relief was extremely painful, and a lot of patients did not stick it.
Morton turned his attention to another substance doing the rounds at student parties. By adding alcohol to sulfuric acid, the students produced a volatile liquid known as sweet oil of vitriol. When inhaled, it resulted in a very decent high. Whoa, this is strong stuff. What is coming out of this is a vapor or liquid that we now know as ether. Ether was a popular alternative to alcohol for teetotalers and was sometimes used in pain-relieving medicines. And it was this pain-killing effect that got Morton interested. Morton started out by using a few drops of ether to numb the mouth. Then he used quite a lot to knock out a spaniel. But what he really needed to do to prove that it was safe and effective was try it on a human. With no other human volunteers to hand, Morton decided to try it out on himself. He got a handkerchief and applied some ether, looked at his watch, and then stuck the handkerchief over his face. A few minutes later, he woke up, but he was unable to move. As he later wrote, "I was terrified that I would die in that position, and the world would laugh at my folly." But the world never got a chance because he made a full recovery, and he was now very, very keen to try this out on someone else. After successful trials on unsuspecting patients, Morton returned to Harvard Medical School. They agreed that Morton should have a second chance to demonstrate pain relief in the daunting domed surgical theatre at Massachusetts General Hospital. The date was set for October the 16th, 1846. Just 16 days' time. On that Friday, this room would have been absolutely packed with medical folk. Many of them expecting, and some of them hoping, that the uppity dentist would fail again. An eminent and extremely sceptical surgeon had been booked for the operation. At 10 a.m., the appointed hour, there was no sign of Morton, so the surgeon prepared to operate. His patient was a young man with an enormous tumour on his neck. He would have been strapped down because he was going to be awake and screaming throughout. But before the surgeon could apply his scalpel to the quivering flesh, Morton came bursting into the room. He was carrying this. It's an ether inhaler, and he'd had it built overnight. No time at all to test it, so he must have been feeling almost as anxious as the patient, but he had no idea if it was going to work. Filling the inhaler with ether, Morton handed it to the patient. He was relying on a complicated and untested system of valves to give the right dose. His future depended on this test succeeding. The Boston surgeons would not give him another chance. When the patient reported feeling a little bit groggy, Morton took it back, and then he turned to the surgeon and said, "Sir, your patient is ready."
They were used to operating on people who were screaming and trying to get off the table. So anything that held you on the table, even if you waved your arms and legs around a bit while it was going on, that was preferable to you being wide awake.
So the surgeon picked up his scalpel and he started to cut. From the patient there came not a sound. The operation was long and complicated, but also successful. At the end, the patient reported that he had felt no more than a scratch. This was an extraordinary moment in the history of surgery, an operation performed without pain. At the end, the surgeon turned to the audience and he said, "Gentlemen, this is no humbug."
There's a wonderful letter from the professor at Harvard to Morton saying everyone will want a share of your great discovery. I'm not trying to take a share, but we do need to give it a name. I would suggest the name anesthesia. And we need to give it a name because everyone throughout the world for the rest of human history will need to talk about what's just happened and what this is.
News spread about ether around the world within 6 months, which, given the communications network at the time, I think was highly significant. What anaesthesia does is act as a bit of a watershed, and the ripples sort of permeate out through society. And there are lots of wider humanitarian movements like the anti-slavery movement, the reform of prisons. You just get the general sense that patience and social tolerance of pain is decreasing.
Pain was no longer an expected and tolerated part of everyday life. It was now something that could and should be minimized. In the 50 years since Zertner's isolation of morphine, a rush of scientific discoveries had replaced old superstitions and beliefs with new knowledge. This would set researchers off hunting for pain-killing drugs in some very unlikely places. By the middle of the 19th century, the mysterious world of herbs and tinctures was being replaced by white powders. And these, thanks to this invention, were in turn being replaced by tablets. We were about to enter the era where chemists could mass produce the sort of painkillers that we now routinely use every day. They were also about to create one of the most addictive substances known to man. And it all began with this stuff, coal tar. Coal tar was a waste product of the burgeoning coal gas industry, and naturally chemists tried to find profitable uses for it.
The availability of coal tar suddenly gives you an enormous new library of starting materials. And by then, chemistry was really kind of taking off. The connectivity, the structures were known. And it was suddenly realized that you might be able to make either the natural products themselves or things which mimic them. That was a real sea change in chemistry.
This sea change in chemistry started as it was to proceed, with a series of mistakes. In 1845, an 18-year-old British chemist tried using coal tar to make quinine, a malaria drug. Instead, he created the first artificial dye, mauve, and made a fortune. Coal tar was clearly worth studying, yet it would take another accident to unlock its pain-killing potential. In this case, a giant cock-up involving two French doctors, Arnold Kahn and Paul Hepp, who were working here at the University of Strasbourg. They were testing chemicals derived from coal tar, which they were testing on patients with intestinal worms. Coal tar had been shown to have antiseptic properties when used on skin. So naturally enough, they wanted to see what effects some of its derivatives had inside the body. Fortunately, they had a ready supply of patients. These were the days when doctors were quite happy to try almost anything on anybody. But even so, I'm amazed they managed to get patients to eat this stuff. It is incredibly pungent. It is naphthalene, the stuff they use these days in mothballs. It did no harm to worms, but it did seem to have an effect. Amazingly enough, one of their patients, who had a fever, reported that his fever went down after he'd eaten this stuff. That was great news. Followed soon afterwards by really bad news. There'd been a mix-up. Whatever the patient had been eating, it wasn't naphthalene. The pharmacy here had made a terrible mistake with the labelling. The patient had actually been eating a completely unknown chemical. It turned out that the chemical that the pharmacist had been accidentally dispensing was this one, acid analyde. Now, who knows how it got here, but it's actually used in the dye industry. But it was a most fortuitous accident. They could have killed the man, but instead, acid analyde, yet another chemical derived from coal tar, was quickly marketed as a profitable fever-reducing drug. And not surprisingly, Kahn and Hepp went on to make a fortune. But the really significant thing about this discovery is what happened next in Germany. There was huge demand for the new headache powders, and clearly a fortune to be made by anyone who could come up with an even better drug. Well, here at the Bayer Dye Works, there was a young and ambitious chemist called Carl Duisbeck, who decided he would give it a go. Bayer's cellars were full of coal tar chemicals like acid analyde, and Duisbeck set out to see which he could convert into drugs. His first discovery, called phenacetin, was very successful. We now know that, like acid analyde, it's converted in the body into paracetamol. Bayer's factory here grew rapidly on the profits, and so did their ambitions. Another substance they got really interested in was salicylic acid. Now, because it's derived from coal tar, they thought originally maybe it's an antiseptic. They rubbed it on the skin and swallowed it. Unfortunately, it didn't kill bugs like typhoid. But what it did do, if you had a fever, is it brought it down, and it certainly made you feel better. Salicylic acid was effective, but it was harsh on the stomach. We use it now to burn off warts. At Bayer's new drug department, research chemist Arthur Eichengrun thought he could see a way of changing the molecule to make it more palatable. Eichengrun suggested a simple chemical modification which would, in time, lead to the production of two incredibly iconic drugs. One of them the world's best-selling painkiller, the other the world's most notorious drug. It started innocently enough. A young chemist in Eichengrun's team set about modifying salicylic acid using an approach that Eichengrun had suggested. The result was crystals of acetyl salicylic acid. Just as predicted, it no longer upset the stomach quite so much. Eichengrun would eventually name this drug aspirin. Simple chemical modifications could clearly make better drugs. Inspired by this, a chemist in the Bayer team took morphine, that powerful painkiller from poppies, and tried the same reaction to see what would happen. The result was a chemical called diamorphine, better known to us as heroin. Thank you very much. Both of these drugs, aspirin and heroin, arrived in front of the chief tester, Heinrich Dreser, and he promptly rejected one of them on the grounds that it was dangerous. Ironically enough, the one he rejected was the aspirin, because he said it was bad for the heart. But he loved heroin. In fact, he named it because of the associations with heroic, powerful, and with his ringing endorsement behind it, heroin was soon being marketed to the world by Bayer. The team at Bayer had accidentally made a far more addictive version of morphine, and naturally, it sold fabulously. Meanwhile, Eichengrun, irritated that his drug aspirin was being overlooked, began secretly to carry out tests. Eichengrun was convinced the new drug was safe, so he got hold of a sample and he tried it. Nothing untoward happened. So next, secretly, he got hold of some Berlin doctors and persuaded them to try it on their patients.
It was given to a small number of doctors and a dentist, and a report came back from the dentist. He said, I gave it to one of my patients who had a fever, but to my astonishment, he said his toothache had been eased by taking the acetyl salicylic acid. It relieved pain.
This was completely unexpected. The original salicylic acid brought down fevers, but it didn't have any effect on toothache. Eichengrun had clearly created something new and powerful. So Eichengrun decided to bypass Dreser and went to the head of research at Bayer. He authorized more tests, and in 1899, a year after Bayer had introduced heroin to a grateful nation, they started marketing this new drug. Aspirin became one of the world's most successful drugs. 40 billion tablets are eaten every year. And it was all thanks to chemists tinkering with an industrial waste product, coal tar.
It was an early illustration of how a simple chemical modification to an existing molecule could make a far superior drug which had additional properties. The additional properties of aspirin are due entirely to the acetyl group. Without the acetyl group, it wouldn't work. And rather amusingly, I keep reading reports of how in ancient times plants containing salicylates were used as painkillers. It's nonsense. They might have been used as painkillers. They didn't work. The acetyl group of aspirin, which was a synthetic drug, had to be present in order to kill pain.
Despite its universal appeal, it took people more than 70 years to understand how aspirin actually works. Turns out, nothing like the opiates, such as morphine. Aspirin acts locally and blocks pain long before it gets to the spinal column. I'm going to demonstrate using my least favourite plant, stinging nettles. Ah, yeah, that hurts. Ooh. Damaged or irritated tissue releases a lot of chemicals, which can help healing, but which also tend to stimulate the pain nerves. You can see the results as red, swollen marks, inflammation. And the same process is often the cause of headache and muscle ache. Aspirin and the other anti-inflammatories all work in the same way, and they block a range of pains. Anti-inflammatories stop your body producing the chemicals it normally does when tissue has been damaged. This not only prevents swelling, but also the release of chemicals that set off the pain nerves. As well as blocking pain, aspirin also blocks the hormones that lead to platelet production, which means that middle-aged men like me take small amounts of it to reduce our risk of getting heart attack, which is pretty ironic when you consider that aspirin was originally rejected on the grounds it is bad for the heart. Chemists had found ways to ensure that we were no longer reliant on plants for our medicines. Modifying simple molecules extracted from coal tar had given us more powerful drugs than the natural world could provide. With misplaced confidence, chemists now decided they were going to try and design drugs from scratch. The hope was they could produce something lucrative with few side effects. The reality was they now unleashed onto a wholly unsuspecting world a whole new Pandora's box of powerful potions. This new phase, trying to make entirely synthetic drugs, started as an attempt to correct the limitations of surgical anesthesia. Ether was an irritant and made people sick. Chloroform, discovered soon after, caused unacceptably high death rates. Perhaps what was needed was a different way of delivering anesthetic chemicals into the body. The hypodermic needle had been invented in the 1840s, and injecting anesthetics via veins seemed promising.
When you breathe in a drug, what you're trying to do is get a level of the drug into the brain. And so if you put it in intravenously, it goes to the brain faster.
So, in 1869, German chemist Oskar Liebreich naively started to experiment with a substance called chloral hydrate, which had been created many years before. The chemical was known to produce chloroform when you added an alkali to it. So Liebreich thought to himself, if I inject this into the blood, which is mildly alkali, then perhaps I will produce chloroform inside the body. He thought it was worth doing. It was certainly a bold thing to do, because instead of trial and error, he was relying on chemical theory. Well, it all seemed to go splendidly at first. He injected it into patients, and they did indeed fall asleep. His reasoning was flawless, but also completely wrong. Chloral hydrate did not produce chloroform when injected into blood, but a form of alcohol, which did not numb feeling or pain. What Liebreich had stumbled upon was not a painkiller, but a drug that put people to sleep. Chloral hydrate was used in some operations, and if a few patients woke up screaming in the middle of it, well, they had no memory of doing so afterwards. A way of putting people to sleep safely and quickly would be a real boon for surgery, but chloral hydrate had its drawbacks.
It upset the veins, it caused phlebitis, irritation in the veins, and the duration of action was very long. So patients were very, very sleepy for a long time. They didn't wake up clear-headed and bounce back to work or anything.
But for those who wanted a long sleep, it was great. Chemists produced a form that could be taken as a pill, the world's first sleeping tablet. And within 10 years, Britons were taking a ton of it every day. chloral hydrate soon entered popular culture. In 1903, a Chicago newspaper reported that a saloon manager had persuaded his employees to put chloral hydrate into the drinks of customers suspected of having money. And then, afterwards, they would rub them. His name, Mickey Finn, became slang for any spiked drink. Now, the importance of chloral hydrate was not just that it was incredibly popular, but it was really one of the first drugs to have been designed from scratch with a specific purpose. The floodgates were open for any imaginative chemist to make a lot of money.
It was a huge incentive. And with their increasing knowledge of which molecules had this sedative effect, they turned out hundreds of new compounds. One of them was to prove a worthy, albeit infamous, successor to chloral hydrate.
Because of its use by criminals, chloral hydrate gained a somewhat notorious reputation. But it would in turn spawn an even more notorious anesthetic, sodium thiopental, otherwise known as the truth drug.
And I'm about to try it.
Sodium thiopental is part of a group of drugs called the barbiturates, and barbiturates were particularly popular in the 1950s and 60s as a form of sleeping pill. They were also very dangerous. Famously, Marilyn Monroe died from a barbiturate overdose. Sodium thiopental was much faster acting than most barbiturates, and that made it a great anesthetic. But oddly enough, it doesn't actually affect pain.
What barbiturates do is slow down all the messages being sent between nerves in the brain and the spinal column. The more barbiturate there is, the harder it is for chemical messages to cross the gaps between one neuron and the next. So, essentially, your whole thinking process slows down until you fall asleep. With thiopental, that happened very quickly indeed. And that was just what the anaesthetists in the 1930s wanted.
Thiopental was developed specifically for getting people to sleep quickly. They knew how to keep people asleep once they got them there with drugs like ether and chloroform, which was still used widely.
As thiopental starts to act, it affects your brain bit by bit. And this is the key to one of its more controversial uses.
The Americans noticed that when patients were in that twilight zone halfway between consciousness and unconsciousness, they became more chatty, disinhibited, and also forgot what they'd been talking about afterwards. They decided this might form the basis for a truth drug, an interrogation drug. Now, I'm going to have a go at trying to maintain the fiction that I am Dr. Michael Mosley, the famous heart surgeon. Okay, so I'm actually feeling quite anxious at the moment. Sodium thiopental has a reputation, not just as a truth drug, but also because it's used in lethal injections.
Anaesthetist Austin Leach will be monitoring my vital signs throughout. These will indicate if my body is feeling pain. Before I take the drug, he wants to see how my heart rate responds when he crunches his knuckles against my chest.
That's quite uncomfortable, yeah. Ooh.
My heart rate jumps from 54 to 64 in response to pain. Now it's time to experience the effects of a light dose of sodium thiopental.
I'll just give a small dose, but quite rapidly.
In, yeah.
It's in now.
Yeah. Doesn't feel like anything.
Well, it hasn't got there yet.
That's probably why I'm not feeling anything. Am I feeling just a bit? Oh, yes, there it goes. Yep, there it is. Blimey, wow. Oh, geez, yeah. That is like, oh, that's like drinking a bottle of champagne.
So, under the influence of thiopental, can I still lie about my job?
I am a cardiac... I'm a cardiac surgeon.
And would you like
I'm
to
a
tell
world-famous cardiac surgeon.
Would you like to tell me what the last operation you carried out was?
It was a bypass. They survived. But, yeah, I was awesome.
And now I'm just going to repeat the pain test.
Yeah, OK.
In your sternum, and tell me how uncomfortable this is.
That hurts, but it doesn't really hurt. I'm kind of aware of it, but I don't care. It's actually quite painful. My heart rate jumps right up. My body is still responding to pain, but bizarrely my brain isn't. It's all very odd. That is so strange. I had just about managed to lie about my job, however unconvincingly. But what would happen if he upped the dose? Oh, yes. The drug's effects aren't predictable, so I don't know what will happen. Dear. Ask me any questions.
So, what is your name?
My name is Michael Mosley.
And what is your profession?
I'm a television producer. Well, executive producer. Well, presenter. Some mix of the three of them.
So, you don't have any history of performing cardiac surgery?
None whatsoever. None whatsoever. I am, without doubt, a good television presenter and a lousy cardiac surgeon. Part of the reason I caved in so quickly is I had this overwhelming urge to tell the truth. It's an odd feeling, quite cathartic. The weird thing is I don't want to lie. You know, I'm feeling so... It's not just that I can't. It's just I feel so benign towards the world that I don't want to do it. I don't want to say I'm Michael Mosley, a cardiac surgeon, because I'm not. So, What else I admitted to under the drug's influence must remain forever secret. From me as well. Afterwards, I realised I had forgotten everything that had happened. Did I confess to the fact that I'm not a cardiac surgeon?
So you can't remember? You can't remember what it was you said about your professional status?
No. And I don't know what I was talking about. Yeah. I feel quite snoozy. I feel like I could probably go to sleep now. And that's the reason thiopentol became such a popular anaesthetic drug. It puts you to sleep quickly and with just a simple injection.
A typical anaesthetic of the 1940s would be getting people off to sleep with an injection of thiopentol and then keeping them asleep with some ether.
It was a triumph for the chemists, a drug that did exactly what it was designed to do. But it was only designed to make people unconscious during surgery, not to stop them feeling pain.
What we're aiming to do is to induce unconsciousness so that the patient has no awareness of what would otherwise be an extremely unpleasant experience for them. To deal with the other aspects, such as pain, we need to give supplementary drugs which are specific painkillers.
So chemists nowadays are concentrating their attentions not on new anaesthetic drugs, but new painkillers.
Because we can build pretty well any molecule of any shape we want now by design, that's the way in which pharmaceutical companies are increasingly oriented. It sounds simple. It's actually very, very hard.
The way chemists create new drugs is essentially the same way they did 100 years ago, when they started experimenting with coal tar. They take simple molecules and build them up into complex ones. These days, you'll not be astonished to hear things are much more high-tech. Most new drugs start out in a so-called compound library, like this one. There are over 3 million different molecules here. With this vast repository of molecules to start from, chemists can put together almost any compound. But there is still the problem of knowing which compounds will be useful. And in the search for the perfect painkiller, a clue to that has come from a most unusual place. A few very rare people born without the ability to feel pain. In the past, they might have ended up in freak shows. But today, some doctors see them as the key to finding a new class of pain-killing drugs.
So we knew long before we even started thinking about drug development that whatever we found in these patients would be a great target for a drug because this would reproduce the pain-free existence they have.
Researchers started by exploring just what people with this condition can or cannot feel.
They could feel when you touch them. They could feel cold. So it also told you from this that the sensation of pain was different to touch, temperature, vibration. You put a vibration on there, they felt it.
This was encouraging because it suggested that pain could be switched off without affecting other nerves. The question was, how? It turns out these people have inherited a faulty gene, which means that their nerves cannot transmit pain signals. While all their other nerves are normal, their pain nerves are unable to send electrical messages. Identifying the problem gene pointed to a particular protein, a protein that is necessary for us to feel pain. Once they'd found the protein, the next thing they had to do was see if they could block its action in normal people. See if they could temporarily switch pain off.
So you can imagine the idea that what we really know about is the shape of the lock. And what you're trying to do is to design a molecular key which will slot in.
The problem with building a molecular key is you may not be selective enough. It's no good switching off pain if you also switch off other essential protein production.
You want to make sure that it is very selective, that it doesn't have major effect on other enzymes in other crucial pathways in the body. Now you have a real lead. Then you have to show that this is really non-toxic.
Drugs that appear to block just that crucial protein are now undergoing a long process of testing. And so far, they are showing great promise. The hope is they will usher in a new era of pain relief.
Now you can see that there is an opportunity to think about a new approach to treatment of pain that also offers hope for millions.
The journey from herbal medicines to synthetic drugs designed and made from scratch has taken a mere 200 years. It has been driven by obsession, need, happy and sometimes less happy accident. And yet some things have not changed. Over the last couple of centuries, we have developed a huge range of pain-killing drugs, from anesthetics to aspirin. But if I was in terrible pain, then the substance I would still use is this, morphine. It is very strange to think that in the 200 years since it was first isolated by Friedrich Zertner, we have developed nothing which is as effective for treating excruciating pain as this extraordinary substance. Painkillers, wonderful though they are really only treating symptoms. In the next programme, I'll be looking at the remarkable stories of those who develop drugs that cure, including the successful attempts to capture and contain the greatest mass murderer in history. If you'd like to take part in the Open University's quiz on pain, or perhaps find out something more about pus and poison, then go to the website below and follow links to the Open University.